the restrictions of helicity on the annihilation process can also be seen in terms of the Lorentz group properties of the various operators involved, and also the properties and classification of various states which are included in this process. And that can be easily seen by performing tensor products of all the factors involved and looking at what that produces. So, when the parities, not parities, when the helicities are opposite, we have the combination of the spinors, say half 0 tensor product with 0 half, which produces the representation half half, and this is the vector representation, and which is the allowed representation for the interaction given by gamma mu a mu. That is the coupling of the electromagnetic current to electron and positron. On the other hand, when the helicities are the same, one will have the tensor product which is combination of two spin half producing 0 and 1, and this 0 0 is a representation for a scalar which is a mass term, and this 1 0 is a representation for f mu nu. So, the corresponding operator will be sigma mu nu f mu nu, and this, for example, can be the anomalous magnetic moment coupling if it exists in the theory. In our case, the anomalous magnetic moment does not appear in the tree level calculation which we have done, but the mass term is still there, and that does contribute. The only thing is that that contribution will be subleading compared to the vector contribution, and the ratio of these two terms is basically just the ratio of energy to mass, which will be large in the particular situations we are dealing with, because the energy is the mass of the muon or larger, and the electron mass is much smaller compared to that. So, this produce the same selection rules, and we will see this features explicitly in the computation of individual terms. So, now let us calculate the various contributions explicitly. The total process has 16 terms which arises for two choices of helicity for each of the 4 fermions involved, and out of these, because of the helicity selection rule, only 4 are non-zero, and even the 4 which are non-zero are further related because of the property of parity, which is obeyed by the theory of quantum electrodynamics, obeys that rule exactly. Which is in terms of the helicity means the processes where R and L are interchanged will be related, rather they will be exactly the same terms which will appear twice, and that means that leads to the relations where we interchange R and L and the answer look the same. So, the process which takes L r to L r will be the same as one which takes R L to R L, and analogous one for the L r to R L being the same as R L to L r. So, these are the only 4 non-zero amplitudes, and parity cuts down the calculation to again only 2 of them being non-zero, and that is the 2 pieces which we will calculate explicitly by evaluating the traces, but now the traces will include the factors of 1 plus or minus gamma 5 exactly. So, the case where both the u and v spinors have the same factor of 1 plus gamma phi, which is an allowed process, produces the combination which is now this particular form. I have just introduced the half 1 plus gamma phi both for the electron wave function as well as for the positron wave function, and this actually corresponds to the helicities being opposite for the electron and the positron. In terms of the u and the v wave functions, the projection operator is the same, 1 half 1 plus gamma phi, and that is according to the conventions which we have set up. And now this can be simplified by noting the fact that every time 1 plus gamma phi goes through a gamma alpha, the 1 plus gamma phi sign change to 1 minus gamma phi, and if 1 minus gamma phi and 1 plus gamma phi come next to each other, they just annihilate themselves. So, one has to just consider the cases where they come next to each other by commuting the operators. For example, whenever this can be taken through the mass terms, then there is only one gamma matrix in between, and 1 plus gamma phi will turn into 1 minus gamma phi when commuting with that gamma matrix, giving 0. So, the mass terms in both this momentum plus mass factors does not contribute, we just have p slash and no m surviving. And so, and a projection operator when gets squared, it gives the same result as well. So, we only have the factor that the projection operator can be counted once and the mass can be deleted. And it becomes smaller, and now this can be explicitly evaluated. There is a factor of 4 from the trace of the gamma matrices, which and this denominators can be combined and pulled out, and now one just have to combine the dot products of various gamma matrices together. We just first evaluate the one part of the 1 plus gamma phi and then the gamma phi part. So, the one part is the trace which we had evaluated earlier, and it just produces mu dotted with p 1 first, then mu dotted with nu, and then mu dotted with p 2, giving this particular result, and the gamma phi is now contracted with 4 gamma matrices, mu p 1 slash, nu p 2 slash, and that has to be evaluated by its own trace definition, and the result is the epsilon symbol multiplied by the 2 momenta with the corresponding indices. So, this is the dominant part of the contribution. Its in terms of magnitude, its order E square divided by m square, and this is the dominant. Contribution. Let us also evaluate the other part, which has the wrong helicity combination and see what comes out of that. So, in that case we had the same factors, it's just one sign of gamma 5 is different. And now, when commuting this 1 plus gamma 5 factors through the gamma matrices, a different combination from the propagators survives. The mass term does contribute, but the p slash plus part produces combinations of 1 plus gamma 5 and 1 minus gamma 5, which annihilate each other. So, that result is just this. Again the 1 plus gamma 5 projection operator when squared gives the same thing again, and we have taken this out. And now, this is a trace of only 2 gamma matrices in one case of the identity, and when gamma 5 contracted with only 2 gamma matrices produces no trace at all. So, the result is actually quite simple. It gives minus half g mu nu. This is in terms of magnitude, it is order 1, and this is a subdominant. So, in doing this explicit calculation, we see little more physical behavior than just counting the helicity as the leading term, and that is we see actually the magnitude of suppression whenever the helicity conservation is violated. So, in general mass term can flip helicity, but that suppresses the amplitude by a factors of m over e, and the square of the amplitude, whichever is in part of this trace, gets suppressed actually by m square by e square. And we see that explicitly in the calculation where the allowed helicity combination is larger by a factor of order e square by m square over the unfavored contribution which comes from mass term flipping the helicity. So, that much for the selection rule, and to do the leading order calculation we will ignore the contributions which are suppressed by factors of mass. So, we will only do the high energy part, which is characterized by the relation that square root of S is much larger than the mu1 mass, and now we square the total TFI square, which has product of two of these traces, all the indices contracted, and in particular we need a contraction of two epsilon symbols, and the explicit result which is required is a contraction of two of the indices of the epsilon symbols, and it can be easily seen that all the pairs have to match completely to produce a non-zero result, and that produces Kronecker deltas in this contraction, gamma equal to lambda and delta equal to tau, or if the combinations is switched around, the epsilon symbols are antisymmetric, and so there is a minus sign, and the overall factor of 2 comes because this alpha beta can be contracted in two different ways because of the permutation possibilities, and the overall sign is negative because we are dealing with Minkowski space time. So, the epsilon with all the upper indices is negative of the epsilon with all the same indices in the lower place. 3 of them produce a minus sign and the fourth one has a plus sign. So, this is the result, and then one has to now just contract two of these traces together. The part of the trace which does not involve the epsilon actually has the same structure as what we dealt with before. It is symmetric under interchange of P1 and P2, and it has either the indices on P1 and P2 or a G mu nu term. So, we can just take the previous result and write it down in this particular context. So, that gives the polarized contributions to the cross section are first just the phase space factors explicitly, and then the contraction terms one by one. So, it gives P 1 dot P 3 and then P 2 dot P 4. These are the result for the symmetric terms. And the antisymmetric epsilon terms produces result which depends on the sign of helicity projection. So, it's either plus or minus, where plus or minus is the same sign which is there in 1 plus or minus gamma phi. So, I am just writing both the result in the same formula, and the interesting point is this Kronecker deltas produce a result which has the same structure as the first line apart from the signs. And here the combination just produces this result. Now, it can be simplified in case of the two independent amplitudes which we have, and that can be easily calculated to be the factors which are nothing but 1 plus cos theta whole thing square or 1 minus cos theta whole square, where the first option is valid for L r going to L r or R L going to R L. And in this particular case, one has to keep in mind that we have assumed a perfectly polarized state. So, there is no averaging factor to be included in the sum over the spins. We have made a specific choice explicitly, and this one is valid for L r going to R L or R L going to L r. And one can easily see that if we add up all the 4 possibilities and divide by 4 to average over the initial helicities of electron and positron gives the earlier result for d sigma d omega unpolarized. So, that is the explicit calculation. We learnt a little bit more about identifying individual terms and seeing the feature of helicity explicitly appearing. One can actually see the features by doing a more elaborate calculation instead of just evaluating the traces, which I have done. So, more detailed calculation shows that these factors of 1 plus or minus cos theta, which are appearing as squared in the cross section, they appear in the calculation of the amplitude itself, and they are a consequence of this helicity properties. And when you square the TFI, of course, you will get the squares of this particular amplitude. So, that is one feature, and other feature which is buried inside this factor is also quite easy to notice, and that is a consequence of the total angular momentum conservation. So, if we have a amplitude LR to LR, it is perfectly okay when theta equal to 0, the angular momentum is just carried on straight over from the initial state to final state. But if we look at the situation for theta equal to pi, then the momentum direction is reversed, and since we are looking at helicities here, the angular momentum has to be taken into account, including the direction of momentum, and so this will vanish at theta equal to pi, because the angular momentum will not be conserved, it is conserved exactly at theta equal to 0 without any suppression factors. For other angles, there will be something in between, and similarly in the flipped case, LR to RL amplitude vanishes at theta equal to 0. So, that explains where this 1 plus cos theta and 1 minus cos theta appears as well. So, that is as much as can be done in this simple fashion in terms of polarization annihilation process, and experiments with polarized E plus E minus beams have indeed been carried out. The experimental polarizations are not perfect, and in that case one has to include these various terms with appropriate weight factors. So, one can actually go all the way from unpolarized case where there are no weight factors, or rather weight factor is uniform for all possibilities, to partially polarized where some contribution is more than the other, to total polarized where one particular contribution dominates over everything else. Okay. So, that is as much as I want to say about calculation of polarized cross sections. Now, I want to illustrate another process which can be obtained by the same machinery which we have set up, and that is a question of analyzing production and decay of bound states. And generically, for processes involving a particle and an antiparticle, there are bound states just below the threshold, because particles and antiparticles with opposite charges, they end up attracting each other. question is, can the formalism which we have set up be used to predict some features of this bound state? The answer is yes, if we are little bit clever. In particular, we need to include the features of bound states on top of the perturbation theory. The perturbation theory per se cannot produce a bound state, it is a natural formalism for dealing with scattering, and we need to sum up a infinite series in scattering if we really want to see the bound states. On the other hand, we can use our experience from non-relativistic quantum mechanics to combine this relativistic scattering theory with the corresponding wave functions described in the non-relativistic language, and the non-relativistic wave functions have to be used explicitly. They will be beyond the perturbation theory, but provided we combine them properly, we can actually predict something for production of bound states. So, what we will assume is that most of these bound states are non-relativistic, and we will assume that that is indeed true for the calculation which we are going to do, and so we will use initial relativistic production of the fermion antifermion pair can be combined with subsequent non-relativistic evolution to a reasonable approximation, and without this strategy, bound states lie outside perturbative framework. So, now let us just explicitly write down some formula which show this structure. So, let me draw the fermion antifermion bound state diagram. Once again, slightly different than what I drew earlier. So, there is electron and positron which annihilate into a virtual photon, but now the f and f bar are not flying away from each other, but they remain together constrained by whatever the force that may be bounding the fermion antifermion pair with each other. And in this case, the f bar system is in L is equal to 0, S is equal to 1 state. We have assumed that the system is non-relativistic. So, L and S can be specified separately. We already saw in the previous analysis that the cross section just above the threshold was isotropic, which meant that the angular momentum involved in that particular case was 0, and the helicity selection rule says that the state will be produced with S is equal to 1, and in particular we still assume that the fermion mass which is produced is much larger than the electron mass. So, the electron helicity rule holds to an excellent approximation, and then the spin state has S equal to 1, and this are called massive vector boson states, and these are the ones which are often the first states to be seen whenever a new particle antiparticle threshold is crossed. They are the easiest to observe because of this various conservation laws involved, and we are looking at the dominant contribution in that particular case. So, let us now give the explicit formula of the wave function which we are going to deal with it. So, let the mass be m, and since we are non-relativistic, this m is approximately 2 times the fermion mass, and the wave function psi of r. In particular, we have already seen that L is equal to 0. So, this object is going to depend only on the magnitude of r and not the direction. So, the various rules for non-relativistic description in terms of this center of mass frame of two identical mass objects specify that we have this relative coordinate is the separation between the F and F bar, the corresponding conjugate momentum, which will be the half of the difference, rather it is just the momentum of one of the objects if you want to use the center of mass frame, and the relation between position and momentum coordinate is the standard rule in non-relativistic quantum mechanics of Fourier transform. So, this specifies the wave function, and we have assumed that it is a bound state of these two objects. What we also need to calculate explicit numbers is a particular convention for normalization, and here we will choose the non-relativistic normalization convention for this wave function, which is the mod psi square integrated over the whole space gives 1. In relativistic normalization, this was proportional to energy, and we are going to use a different convention. One has to check it out that all these conventions are accompanied by appropriate factors of volume, the box normalization which we had used earlier for using plane waves versus this overall normalization which corresponds to a bound state, and once that is done consistently, all the factors of the box normalization has to cancel out of the final formula. And then now we can put together the transition matrix element combining the two stage process, first a relativistic production followed by formation of a bound state, and that gives the amplitude for E plus E minus going to some bound state denoted by B, which will be the overlap of the bound state wave function with whatever is produced by the relativistic annihilation process, and I will take this overlap in the momentum space. So, the first process E plus E minus to F F bar produces this matrix element T F I, and then the next one basically just projects that part of it which can form a bound state. And this result turns out to be reasonably simple in the spatial case which we are dealing with, because close to the threshold this T F I is essentially a constant. It does not even depend on the momentum vector. The factors of various momenta which we saw in the calculation of cross section, all of them actually came from the phase space integrals of delta function in this near threshold situation. And so, if TFI is going to be independent of k, it is isotropic, so it does not depend on direction of k, but it is also independent of the magnitude of k near threshold, then we just have an integral of psi star over the whole space, and that is nothing but the inverse Fourier transform with a phase factor corresponding to 0. So, this gives nothing but psi star at origin in the position space multiply by this object, which is independent of k . So, we have this rather simple rule. So, all we have is now just the wave function at the origin, which is characterized by the type of bound state in the non-relativistic calculation, and the relativistic perturbative factor which we have already calculated before, and just put them together. So, this psi star 0 must be obtained from non-relativistic analysis of FF bar bound state, and that will depend on what is the force holding the F and F bar together. One has to solve the Schrodinger equation and calculate what is the wave function at the origin, and that is not calculable in the machinery which we have introduced so far, but treating it as a parameter we can calculate everything else, and so the total cross section will depend on whatever this wave function at the origin is in the actual system, or turning it around, one can use the measurement of the total cross section to estimate the wave function at the origin of the bound state. And in S waves, interaction, this is the only parameter needed for the annihilation process. All the features are tied together. Annihilation means the particle and antiparticles have to come on top of each other. That can happen only in S wave. The other waves have no amplitude at the origin, and so the amplitude at the origin psi star 0 actually dictates the probability of F and F bar coming together on top of each other, and L equal to 0 dynamics of the process guarantees that that is the only parameter which should be present in the calculation. So, now we can put together the various factors once again. again we will treat the unpolarized vector boson production here it is no longer the differential cross section, there is only one object in the final state and we just get directly the total production cross section by putting in all the constraints and doing the delta function integrals. So, that result is the overall normalizations of 2 pi raised to 4, then the normalization of the initial state electrons which are still relativistic, the matrix element square which we have written down above, and now there is only one differential element in the final state phase space, and then there is a overall normalization dividing by the flux, and this can be now very easily simplified. The momentum integral is rather trivial, so we will just get 2 pi delta function of energy alone then there is a factors of E1, E2 and m e square, and then the value for the flux. We calculated it earlier and the result was E1 E2 divided by 2 E1 magnitude of P1, and that is the expression. The momentum integral is already gone, but the energy wave function, the energy delta function still remains, and one can keep the various things together in the form which they are, and just write down the final answer. This various factors are easily taken care of. The energy factors cancels, E1 P1 survives. I forgot here this TFI square, and so the result can be written as cancels out various things. So, there is pi divided by E1 P1, then there is m e square, and then the matrix element square, and the delta function can now be written as square root of S, which is the center of mass energy, minus m. And this is the condensed result for the cross section, now one can calculate this TFI explicitly in terms of the results which we obtained earlier and reduce this to explicit formula in terms of the fine structure constants and the wave function at the origin.